Okay, so um, hi, how are you? This is Ali, and I'm talking about K-means clustering and association rules. In this video, I'm going to talk about K-means clustering. So K-means clustering is an algorithm, which is a super unsupervised algorithm that works on unlabeled data, and enables you to find groups of your data which falls into the same category based on a measure of similarity. So if you have some documents that you want to group them by topic, or you have some samples that you want to group them by purchase patterns, anything, you can use this algorithm. Sometimes it's an algorithm on its own to find different patterns in your data. Sometimes it's an algorithm that could be used before doing an actual classification. So what it does is that it sorts algorithms into different groups based on similarity. And the characteristic of this algorithm is that the items in each cluster are more similar to each other, and the items in different clusters are more different than each other. And that distance is something that we define. We'll talk about that soon. So something to keep in mind is that this is not a predictive method. It just finds similarities and relationships. So it doesn't tell you which sample belongs to which category. That's KNN. So K-means finds different clusters without having any information about the classes. So actually, K-means is one of these algorithms. There are many more, but this is the main one. So let's focus on this K-means, which is a specific type of clustering algorithm. As I mentioned, it's unsupervised learning. It works on unlabeled data. And what it does is that it takes n observations as input, like n samples, and then maps them into K clusters. You have to give it the K. Sometimes you have to find the best value of K, but that's usually the case. The input to this algorithm should be numerical. So it doesn't work on categorical values and features. You have to convert them into numerical data. And there should be a distance metric defined over the variable space. So Euclidean distance, the one that we provided an example, is one of the main trivial examples of a distance. You could use any other distance that you like, either a Manhattan distance or anything else. But Euclidean's distance is something that you could start with. The output of this algorithm is the centroids, or the centers of each cluster, and the assignment of each input datum to that specific cluster. So each sample is assigned to a centroid, and that is what you get. So the use cases of K-means is that first, it's an exploratory technique. So it helps you to explore the data and see how many groups there might be. So what is the structure? What is the properties of each structure? Sometimes it's used as a prelude to the classification. So if you want to discover the classes, you don't know how many classes you have, then you could provide your data on label to K-means clustering. It gives you an idea of how many classes you may have and what are the properties of them. So some examples are like you provide the height, weight, and average lifespan of animals, and it tells you what different species there might be. Or you provide household income, yearly purchase amount in dollars, number of household members, and it tries to categorize, create some categories of how many different individuals, like families, you have in your data. So that's going to help you like create clusters and different groups without knowing the actual classes. So the algorithm is very simple, and it's very easy to implement. So the first step is that you choose K. So you have to give it the K. Sometimes you go over many different Ks, which is the number of centroids. And sometimes you could just like, I don't know, start with a random k, and then like in an advanced k-means algorithm, you could create another k like randomly, and then try to split clusters that are too close to each other, or remove clusters that do not have many variables. But by default, you just choose your own k and give it to the algorithm as a hyperparameter. So you choose k, and then what the algorithm does is that it selects k random centroids. So it goes over and randomly selects these centroids. Like in this case, k is equal to 3. So it chooses 3 centroids just randomly over your data. Here the data looks like it's 2D. So we have 2 dimensions, and the number of dimensions equals to 2. So the next step is that it assigns records to the cluster with the closest centroid. So it looks at the data and those centroids and goes over each of these samples and calculates the distance, the similarity between that specific sample and each centroid. And similar to k-means, it tries to assign to each sample a centroid that is very close to that. For example, for this specific one, it calculates the distance between that sample and this centroid, that sample and this centroid, and that sample and that centroid. So this one is basically the closest one. So it chooses that as the closest centroid and assigns that sample to that centroid. But it might not, because the centroids are random. It's not going to be quite optimal. So there are more steps here. Then in step 3, it recalculates the resulting centroid. So it calculates the mean value of each centroid of all the records that are in each cluster. For example, here you see all these different samples that are assigned, but when you actually calculate the mean value, the center of those samples, this is the actual center of those samples. This other one is, this blue one is the center, the actual center of those assigned samples. So it tries to refine and find a better mean for those samples. So then what it does, it creates those new centroids and then repeats step 2 and 3. So what happens in step 2 and 3 is that it tries to find samples that are it tries to assign samples that are closest to those centroids, and then it starts to find samples that are close to that centroid, and you could see the result of that here. So this is the new centroids, and we have some new assignments here. Some of the assignments change in this process. For example, look at here. Look at this sample. Previously, it was assigned to that random centroid, but now that the center mean actually changed to the new place, that sample is now assigned to this new centroid, this one. Okay, so we repeat these 2 steps, like assigning samples to centroids and then adjusting like moving the centroids to the center of those kind of clusters. And at the end, we stop when record assignments no longer change. So the mean will be kind of the mean could change sometimes, but it may wobble a little bit, but at some point, everything stabilizes and no records are changed. That's where we stop. So if you want to pick the best value for k, it's hard. Sometimes you choose the value of k based on your knowledge. Like sometimes you say, okay, I think there's 3 groups, but I don't know how these different groups, how records are assigned to those groups, or what are the centers of them. But sometimes you could use this kind of heuristic approach that you go and try different number of Ks. So what you do is that you run your algorithm for different Ks, 1, 2, 3, and so far. And what you do is that you calculate a metric which is called the within sum of squares, or WSS. So within sum of squares is the sum of the distances between the sum of distance between each value, each sample in each cluster, and the cluster itself. So CI is the centroid of the ith cluster. So, okay, sorry. So CI is the centroid of I cluster, and you just want to know how spread your samples are around that cluster. And after, like, if you have only one cluster, you could see that the distances around that cluster, if this is your single cluster and you have all these different data, you can see that, well, the distances are quite high. But if you change that into maybe two clusters, two centroids, you can see that the average distance, the sum of all these distances, are going to be decreased. So if you have too many, like that's your data, and then you have like maybe a lot of different centroids, then the distances might be, yeah, that one belongs to that one. So the distances decrease. So as the number of centroids increase, the sum of the distances between the samples and the centroids decrease. But ultimately, the closer that the smallest number of distances is when you choose K as the number of samples you have. So it's going to be 0. Like if you have like n samples and then you have n centroids, then the centroids will fall into your sample data itself, right? So if this is your data, then you could say, okay, this is my C1, this is C2, C3, C4. And what happens is that the distance between them are 0, but there's no clustering, like you haven't done anything. So we should find a balance between the number of centroids or actual clusters and something that is meaningful for us. One good approach, which is heuristic, is that you draw these WSS, which is the total within sum of a square, over the number of clusters. You draw this, plot this diagram, and you take a look at it to see where it stops going down quite sharply and it starts to flatten out. So that's kind of like the elbow of this plot. So from 1 to 2, I think that's a sharp drop. So we want to choose 2. 2 to 3 is still a sharp drop. 3 to 4 is still sharp. After 4, 5, 6, 7, and so on, you see that it's kind of flattens out. Like it isn't dropping very quite sharply. It's heuristic, so there might be better ways. Like you might choose a different one than I could choose. But this is a way that you could find the best K. Just one important thing is that scaling is very important. So we'll talk about that. Let's see how I'll talk about that one in the next slide. So let's talk about diagnostics and how we could see what are the problems with the model. You look at the data, and if you see that the clusters look separated at some of the plots, like they're far away from each other, then you could use some pairwise plots, something similar to this. So this is a pairwise plot. You could use this pairwise plot and look and see how different clusters are actually separated from each other based on 2 variables. So this is for example, an online retailer. The purchase frequency versus return rate. lifetime customer value over return rate. For example, let's go on purchase frequency or return rate. Like, for example, Costco. It is some people lifetime customer value is the benefit of a customer to the business, and return rate is how many times they're actually returning their products. So when you look at these two different plots, you will see that the customer, like the return rate, if it is too high, you see all those values are like return rates that are kind of too high. The lifetime value is not quite high for that specific retailer. But so although, and another thing that you could see here is that the purchase frequency, the more a person purchases, the more they return. So sometimes there are some groups of customers that do not purchase a lot of items, but they return lower as well. People who purchase a lot, they return more. And the lifetime value of that customers who purchase more because they return more might not be that ideal. So these are different groups that you could see and find. And why do we care about this information? Because we can address different people differently. Like we could say, well, these are like some of these groups, for example, here, purchase frequency. So we could see that we want to focus that a specific group, send them some flyers, and they probably come and purchase more. We don't want to send flyers to these people who are purchasing frequently, or vice versa. Like that's a marketing decision. You could provide coupons to these guys. You may provide, I don't know, multiple items, like a different coupon that says, like, if you buy 10, you get 10 free. Like that's Costco, right? So it's a different marketing strategy. So finding these clusters is quite helpful. So if these diagrams help you see if these categories are separated in at least some of the plots. So, and we could see that, yeah, these clusters, these groups are perfectly separated in at least 2 of the 3. Here it is kind of, but not perfectly. So yeah. So now that's one thing that you want to take a look at. And the other thing is you want to know if you have any clusters with a few data points. So if some of your clusters have only a few data points, try decreasing the value of k. So you might have too many clusters. Are there some splits in the variable that you would expect, but you do not see? So you expect that there should be 2 groups here, but it's actually 1 group. So try to increase the value of k so those groups could be created. Are some of these centroids close to each other? Then if they're so close, then maybe you want to decrease the value of k and make sure that they are just 1 group. Do the means of the variables like they vary a lot across the cluster? Try decreasing the value of k, because then you have bigger centroids. So at the end, there are some ways that you could see if you want to choose or caution in choosing k-means. Choose k-means because it's very simple to implement. It's easy to implement. It's easy to assign new data to existing cluster. You could just simply add some data and find out where it is in that cluster. So it's concise output. The coordinates are precisely given to do that. Well, this is the centroid of this cluster. So it's very easy to understand. Some cautions. It does not handle categorical variables, so you have to convert categorical variables. It's insensitive to initialization and first guess. So the first assignment of the k, it could kind of define the final cluster. So if you run it several times, there is a chance that the assignments could be different. And so variables should all be measures on similar scales and compatible scales. So this is very important. This is what I wanted to talk about. So k-means is not a scale invariant. We talked about normalization. So normalization is quite important, and actually standardization is very important here in k-means. So you have to make sure that your data is standardized so that like the scales and differences between each feature is actually comparable to another feature. Otherwise, what happens is that your data, your variables, one variable could be more important than the other variable, and then they're not put into clusters based on just the whole variable as a holistic group. It's going to be the variables that have a different scale, like the distance between each feature is more than another feature that has a small distance between them, then that group and that clustering will work more based on that specific feature that has like a bigger interval in general. So make sure you do normalization and standardization, one of them, for this specific algorithm. So it's not a scale invariant. So K should be decided. If you have a wrong guess, sometimes you guess poor results, that's a caution. And the actual clusters tends to be round clusters. So like they look like this. That's because of the Euclidean distance, right? So if you choose a different distance, then that could change a little bit. Okay, so that's it for now, and thank you for listening. If you had any questions, please let me know. Okay, thank you.